Hello dear students, today we will discuss second law of thermodynamics. So let's start. So before going to start the statement made by Kelvin Clausius statement, at first we define certain terminologies. The first one is heat engine cycle. So heat engine cycle is the thermodynamic cycle in which there is a net heat transfer to the system and net work transfer from the system. The system which executes a heat engine cycle is called heat engine. For example, heat engine may be in a form of mass containing in a piston cylinder arrangement like this, or it may be a steam power plant. In the steam power plant, you will get one boiler where steam is boiled and the steam is passed through the turbine. After that, the steam comes to the condenser, then condensate pass to the pump, and again it moves to the boiler. Let's come to the efficiency of a heat engine. The function of heat engine is to produce work continuously at the expense of heat input to it. Therefore, efficiency of a heat engine is given by net work output of the cycle divided by total heat supply to the cycle. So net work divided by Q. Q is the total heat supply. This is also known as thermal efficiency of a heat engine cycle. So let's talk about another terminology, thermal energy reservoir, TRE. A thermal energy reservoir is defined as a large body of infinite heat capacity which is capable of absorbing or rejecting an unlimited quantity of heat without suffering appreciable changes in its thermodynamics property. The thermal energy reservoir from which heat is transferred to the system operating in a heat engine cycle is called source. This is the source where heat engine derive the heat. The thermal energy reservoir to which heat, this is the Q, heat Q is rejected from the system to the during the cycle is called sink. The temperature furnace where fuel is continuously burned and is a typical example of source, and typical example of sink is a river or maybe sea or maybe atmosphere itself. Let's come to another terminology, mechanical energy reservoir. A mechanical energy reservoir is the large body enclosed by an adiabatic wall capable of storing work as a potential energy. Let's come to another one. This is called reverse heat engine. It is an engine operating in a reverse way. That is, receiving heat from the low temperature and discharge the heat to the high temperature. When a reversible process is achieved, all the energy interaction associated with the process are reversed in direction, but remain same in magnitude. Example of reverse heat engine are heat pump and refrigerator. So let's talk about refrigerator in a nutshell. A refrigerator is a device which is operating in a cycle remove heat continuously from a body to maintain the body at a temperature lower than the temperature of the surrounding, that is atmospheric temperature, and reject the heat to the atmosphere with the help of some mechanical work input like compressor work. So here is the example. A body you have to maintain at a temperature, and it will take that heat which is coming out from the outside by this refrigerator by doing some work that is called compressor work, and give the heat to the higher temperature. So performance of a refrigerator is represented by the terminology called coefficient of performance, which is the ratio of desired effect for here it is the refrigerating effect to the work input. So for COP for refrigerator will be refrigerating effect divided by work output. So refrigerating effect denoted by Q2, and work input will be Q1 minus Q2, where Q1 heat rejected to the atmosphere and Q2 heat removed from the cold body. Let's come to heat pump. It is a device in which heat supplied continuously to the body, maintaining the body at higher temperature than the temperature of the surrounding by absorbing heat from the atmosphere with the help of mechanical work output. So this is the typical diagram of heat pump. Let's come to the COP of a heat pump. So COP of a heat pump, desired effect here is a heating effect, and work input is W is denoted by Q1 divided by Q1 minus Q2, where Q1 is the heat supply to the hot body to maintain the temperature of the body above atmosphere, and Q2 is the heat supply to the engine. Now if you go to the relationship between COP of a heat pump and heat engine, you will get COP of a heat pump, that is Q1 divided by Q1 minus Q2 is equal to, again you can rearrange this one by putting Q1 minus Q2 plus Q2 like that. You will get this equation, Q1 minus Q2, Q1 minus Q2 it became 1, and it became Q2 minus divided by Q1 minus Q2, which is a COP of a refrigerator. So COP of a heat pump is equal to 1 plus COP of a refrigerator. Thank you very much. Hope you will enjoy the video. Thank you. Stay safe.